All right, so maybe let's start again. So before doing so, let me just... So I think you should all have received a mail explaining that we changed slightly the program. So we have moved the session tomorrow after lunch at 1:30 instead of 2. And we have also put the poster session at 3:45. The reason is that we have a time window that seems okay for the weather tomorrow. So we'll move to the Pane Quotidiano, which is the place where we'll have the social event, which is on the seashore. We'll bring you there after a nice walk. So we'll leave here around 4:45. So we'll have a 1-hour poster session from 3:45 to 4:45. So please make sure that during lunch or whenever you have time, you put your poster there on time. So because we have shortened a bit everything, so it would be good that it's ready at 3:45. And at 4:45, we'll make signs like this, and you just follow us. We'll move. We'll start the hike from there, and it will take something like 50 minutes to reach the place where you will have refreshments and whatever you need to eat. Okay. Perfect. All right. So that being said, let's restart. So we have our first talk by Mauro Pastore, who is a local, who is going to discuss the statistical mechanics of shallow neural networks.
Thanks, John. Thanks for the invitation. Today I would like to share some work I have been doing recently on the generalization capabilities of shallow neural networks. I'm a physicist, so I will have a statistical mechanics point of view of this kind of problem. I will use tools from physics rather than the more formal approaches we heard about this morning. So this is the outline of my talk. I will spend a few words explaining what is my motivation in studying this kind of problem. In particular, I will try to convey the idea that I would like to understand how feature learning occurs and in which way it is different than older approaches like kernel tricks in support vector machines. I will define what I mean by feature learning in this first motivation part of my talk. Then I will present the statistical mechanics of a null model of feature learning, that is the random feature model. And I will highlight some technical steps that I need to arrive at the results in this setting. The results means understand how this model generalizes. And then I will consider instead the case where I'm really learning a fully connected shallow neural network, and I will look in particular at a regime where I claim that feature learning is occurring, and I will present the result about this. So let me explain my motivation. As you know, multi-layer neural networks, even the simplest one, fully connected multi-layer perceptrons, can implement nonlinear decision boundaries in input space. In this case, you have a nonlinear instance of a training set to learn, where this is supervised learning. You have labels to learn in this kind of XOR setting. And you see that with 4 the neurons, you train the machine, and the machine is able to learn a nonlinear decision boundary. Okay, this is fine. And it's interesting because the neurons learn features about this data set. Features means relevant statistics that are correlated with the labels of the inputs. This is nice, but okay, there are other ways to learn nonlinear decision boundary for a given instance of a training set. For example, you can do a kernel trick. So you first embed your data in higher dimensions. For example, here is the dimension of all the quadratic combination you can do with the components of the data. And of course, this is XOR. So you just need one of these combinations to understand the rule of this supervised learning instance. So what is the connection between these two approaches? So these second approaches I presented, it's basically a kernel machine. And you see that here the learning is linear in the parameters that you have to learn. After you did the embedding, then you just need to learn an hyperplane in this feature space that is able to solve, to do the classification task you are asking for. The problem is that, okay, this setting is nice because it's convex in the parameters you want to learn, but you don't know a priori which one is the features that is assigning the labels. Okay, so in this case, XOR, and you see by eye that the product between the components is the one assigning labels, but in general, you don't know this a priori. So to find the correct combination of inputs that is assigning the labels, you need just to list a lot of features, of possible features. I hope that one of them is the one that is assigning the labels. While in the previous case, this job is done in a sort of automated way by the neural network itself. So the neurons are learning the important combination that is the one assigning the labels. Okay, so answering what is the connection is non-trivial because it has been proven that fully connected neural networks, for example, that are supposed to work like this to learn features, instead are very similar to this kind of models, in particular asymptotic regime, for example, the infinite width we heard about this morning. So, okay, this is my idea, and the idea is to understand when there is feature learning and when instead there is this kind of kernel way of learning rules. And this is the star of my talk. It's a two-layer perceptron, fully connected, if you want, where I have inner weights W and readout weights V. Here, I'm using this slide to fix conventions. I'm using D for the input dimension and K for the feature space dimension, so the number of hidden neurons. And sigma is the nonlinear activation function. So we would like to answer the question I wrote there. How does this network generalize? Okay. And the first thing we do is to study this null model of feature learning, when no feature learning can occur because the inner weights are fixed and random. Okay? So here I'm taking an input point, x. I'm embedding in it in a k-dimensional space, applying a nonlinearity, and then I would like to learn a v that is able to fit a certain rule that I'm going to define in the next slide. So there are many works about this. I will present just my version of this kind of calculations. Some of them dates back to the 90s. And this is the generative model of the data that I'm considering. So I'm putting myself in a teacher-student setting, which is similar to what we heard this morning. So I would like to have a generative model of the data in order to access some average properties of this kind of model. In particular, I'm taking Gaussian inputs, IAD and standard. And as a teacher, assigning labels, I'm taking a polynomial. So the teacher is taking combinations, monomials of the components of the input and assigning rules through the labels I'm sending labels through the rule I'm writing there. That is taking these tensors, the tensor product of the input components, contracting them with the tensors that are the ones defining the teacher, and then assigning the label according to, for example, the sign of the output of this thing. Okay, so nu is a polynomial in the input components. The parameters of these polynomials are this theta, that are at the end the things that the student would be able, would learn, let's say, in some sense. Okay, and I have a training set of output-input pairs. N is the size of the training set. And I would like to consider the polynomial asymptotics, where the number of hidden neurons of the students is scaling like a power of the input dimension, and the size of the training set is also scaling like a power of the input dimension with, in principle, mismatched exponents. Okay, so this is the setting. And I would like to do empirical risk minimization. So I would like to train our model. So the only parameters that I can train are the readout weights, because the inner weights are random and fixed. I have a certain loss that is measuring how much the model is doing with respect to the true labels. So this L is just a loss function. I'm summing over all the training examples. And then I'm putting an L2 regularization in this second term of the loss. Once I know V star, I can evaluate stuff like the generalization error, and you see that the generalization error depends on the distribution of nu and lambda, where nu is essentially the teacher and lambda is the student, evaluated in the solution of the empirical risk minimization problem. You see that V star is a complicated function of the dataset, because V star is the solution of that argmin problem. So let's say a convenient way to write it is as a zero temperature configuration of a statistical mechanics ensemble. Okay, so instead of writing V star, I'm writing the average over a certain ensemble, and then I take the temperature going to 0, which is where you see that where this measure is concentrating over the solution of the empirical risk minimization problem. Okay, this is a way to write that probability distribution. That is the one that helps me to access generalization error and this kind of stuff. Okay, and you see that this is a statistical mechanics ensemble where the training set and the random features and the teacher features are entering in a quenched way. Okay, so if you are coming from spin glasses, you know that this kind of problem are hard to solve, because if you want to do the thermodynamics of this kind of problem, you would like to learn the average value of the free energy, for example, the free entropy, for example, of these problems. But let's say the average of the log is not the log of the average. Okay, so you need a way to evaluate the quenched average of logarithm of the partition function, for example. And the way to do that is traditionally using the replica trick. So you take S times the partition function, you average S times this replicated partition function, and then you send the number of replicas to 0. Okay? You see that as long as S is an integer, this makes sense, because it's just S times the original system. I just have to take S times a vector V, etc., and all the replicas are not speaking to each other. So the idea is that now I can average here over the disorder. I would like to write everything in terms of, let's say, few order parameters that are coupling different replicas. And then I do this crazy limit of taking the number of replicas to 0. The way to do that, because the order parameters will be matrices in the replica indices, is to find a clever, let's say, a parameterization of these matrices in such a way that the number of replicas then is just a parameter, and I can continue it to do the replica limit. Okay? This is a flash course on replicas. So after replicating, the thing I have to evaluate is a replicated version of the distribution I showed you before. So this distribution is the distribution of the teacher and the replicated students with respect of the input x at given weights. This is the kind of probability distribution I have to evaluate to solve the problem. And what do we do? Well, let's see how lambda is defined. Lambda is our model, no? So it's a readout vector applied to a nonlinearity, applied element-wise to some certain pre-activations, which are the H vectors here. And the H vectors, you see that at given f, the H vectors are Gaussian variables, because the x's are. Okay? So these are linear combination of Gaussian variables. So they are Gaussian, with covariance C, which is just the combination of the random features entering there. Okay? So here I have an high-dimensional sum of nonlinear function of correlating Gaussian variables. You agree? So the claim is that the distribution of lambda is Gaussian as well, by some sort of central limit. You see that if I didn't have the nonlinearity, so if sigma was the identity map, then these were just, the lambdas were just a linear combination of Gaussians, which is Gaussian, at any value of kappa, etc. If this covariance of the preactivation were the identity matrix, then this sum were just the sum of uncorrelated random variables, which is also Gaussian by central limit, standard central limit. When I have both the nonlinearity and the correlation between the preactivations, this thing is a bit tricky. But at least in the setting on the random features has been proved. And OK, I hope that you believe that this can work. In any case, this is a heuristic way of obtaining results, and we will check the results with the numerics at the end. OK, so if you believe me that these things are Gaussian, the only thing that we need to do is to evaluate the first and second moments of these random variables. Let's say the first moment, OK, the mean is 3 is kind of trivial. But the covariance is, I have a teacher-student covariance, that is the M, and a student-student covariance, that is the Q. And what I have to do to evaluate the Q is just to evaluate this expectation between two different activation functions evaluated at different preactivations. Okay? And this I can do. Okay? Let's say, knowing the fact that the HI are correlated Gaussian variables with covariance C, I can write this expectation as an infinite series of Hadamard powers of the covariance of the preactivations. The coefficient mu entering this series are the one coming from the Hermite expansion of the nonlinear activation function that I showed you at the beginning. I don't have to define the Hermite polynomials because we heard all about them this morning. Okay, so this is a result coming from the 1800s, and it's due to the fact that you can diagonalize the measure of the preactivations in such a way that you can do the expectation over HI and HJ separately. But if you do that, you find this infinite series there. OK, as long as it's an infinite series, this is not helping much. I have to do some reasoning to truncate this series in a clever way. And I can reason in this way. Well, Cij is essentially a V-shot matrix. You can see it here. This is Gaussian, this is Gaussian, this is the inner product of two Gaussians summed over the inner index. So it's a V-shot matrix. What does the Lth power of a V-shot matrix do? Well, let's see. Cij is, being a V-shot matrix, is order 1 if I is equal to j, or order 1 over square root d if I is different than j. You agree? Now, if k, which is the index, it's the dimension of these indices, is scaling like d, this matrix has a non-trivial spectrum because you have a lot of small off-diagonal numbers that combine together gives the non-trivial spectrum different from the identity. And you get the Marchenko-Pastore law, etc. What happens when Cij to the L, you apply the same argument? Well, you have that the diagonal is still order 1, and the off-diagonal is order d to the minus L over 2. Now, these numbers will be always too small to make the spectrum of this matrix different than the identity if k is greater than so here I have L is greater than kappa, where kappa, let's say, I'm saying that small kappa is going like d to the big kappa. Okay, so if this power is too big with respect to the dimension of the matrix, then essentially this matrix is the identity. Because I don't have enough numbers that are small outside the diagonal to have something different than the identity. Which is the reason why here I'm truncating up to kappa, where this capital kappa is the power of k with respect to t. Okay? Interrupt me if something is weird or... And what's the rest? Well, once every single power is a delta ij, then the rest is just a summation of the resulting Hermite coefficients. Okay, this thing means that essentially our original model, our lambda, which is the nonlinear function applied to the random features and then with the readouts, is equivalent to a polynomial model up to order kappa plus noise. By equivalent, I mean that the statistics of this object is the same as the statistics of the original lambda. Because if I take the covariance of this, and I take expectation with respect of x, I get exactly that covariance there. Okay? Where the coefficients of this effective polynomial model are just the contraction of the readouts with tensor powers of the random features. Okay? This is just the let's say, the essential point that you need to solve this theory with replicas, and you do. And with this result, you get this kind of prediction for the generalization error. So let me explain this plot starting from the right, which is the easy thing to do. So here I'm plotting the generalization error with respect to the number of points in your training set. And I'm fixing the number of hidden neurons up to a certain value that I'm calling kappa. And here it's 10 to the 4. When you are on the right of this peak, you have much more data than parameters. Okay, so you would like to learn a lot of stuff, but you are limited by the number of parameters you have. You have only kappa readout parameters to learn. And the best you can do is to learn a polynomial order kappa, where kappa is this kappa here. Then assume you decrease the number of training points you have. What happens? Well, you see that because of the random features, the embedding in either dimension is a polynomial plus noise. And this noise is coming with an index mu. It means that with every point, you have more noise. And this more noise is due to the fact that you are embedding with a random matrix, and the higher order terms are acting as noise, white noise in this case. So here, essentially, you have an interpolation peak of that noise. You have enough parameter to, let's say, learn the noise by heart, which means that you're doing bad at generalizing. Okay? While here, because you have much less parameter than data, you have to forget the noise, and so you generalize better. What happens below? Well, below you have much less data than parameters. So why you are not simply doing 1/2 because you are overfitting? Well, there the model is learning as a kernel machine, essentially. So you can write the model, the best way I can explain this is that you can write the model, the training procedure in its dual form. You solve it with the support vector machine algorithm. You solve it by means of support vectors. The support vectors cannot be bigger, cannot be more than the number of data you have. And the rest of the parameters you have that are much more in principle are just regularized. It's irrelevant how many of them you have, because the solution you can write in terms only of the support vector, which are the ones that are closer to the decision boundary. And you learn first the linear part of the teacher when you have the data. Then you learn the quadratic part of the teacher when you have the square data, and so on. So you have this staircase behavior of the generalization error. This is nothing new. This thing was okay. This is the order parameters. You see that the student is aligning essentially with the L tensor defining the teacher. And this overlap between teacher and student, it's becoming, it's saturating at different values of the powers of data you have. So at first, when you have the number of data, you learn the first tensor, which is a vector. When you have this square number of data, you learn the second term, which is a matrix, and go on. And this kind of behavior, I was saying, it's known since the 90s. These are works by statistical physicists working in machine learning early on. And you see that they saw this kind of behavior in kernel machines. And has been, of course, reproposed due to this motivation of studying deep learning models in the infinite width regime. It has been rediscovered in the recently, let's say, and it has been a lot of stuff have been proven rigorously in the math setting. And this basically the take-home message of the first part. So you see that random feature models in this polynomial regime learn as polynomial models. The degree of the effective polynomial that you can learn is given by the minimum between the scaling of the training set and the scaling of the number of parameters you have. The higher order terms in the expansion are just noise, which is ultimately responsible for the interpolation peak. And with a StatMech approach, you can find the order parameters that are saturating in each regime. So this is for the first part. If there are questions about this, it's the right time to ask them. Otherwise, I pass to the second part. Let's go. Second part, I would like to learn everything. Same model as before. Now I have W's instead of a F, and W's are also learnable. We will do Bayesian learning that I will define in a second. Here, everything is defined as before, so I don't think I have to explain anything. So for the moment, let me consider the simplest case of generative model of the data where the teacher assigning labels is the same as the student. So it is a neural network with matching architecture. So I'm using the same lambda to define the teacher. And the teacher weights are sampled from the priors that also the student has. And then I add some noise to the teacher labels with variance delta. And again, I have n points in the training set, and the student and the teacher's width is k. Notice that now the number of parameters is k times d, because I'm learning also the w, the inner weights. And the student is learning this teacher through Bayesian learning. So its weights are obtained from the posterior distribution of its weights given the data. And the posterior distribution is, the posterior distribution with a Gaussian likelihood of the labels. Okay? Clear? So notice that here, basically, the students knows everything about the teacher except the actual instance of the weights of the teacher. He knows the priors by which the weights of the teacher has been taken. He knows the variance of the teacher because the Gaussian likelihood is taken with that variance. The only thing that the student doesn't know is the W0, V0. Okay, so this is an optimal situation for the student. And from the posterior, I can define the partition function, which is just the normalization of this measure, and evaluate statistical mechanics quantities like the free entropy or the mutual information that is coming from the free entropy. Knowing in particular the free entropy, I know the generalization error. In this setting, because I'm working at finite temperature, I can define different generalization errors. For example, here is the generalization error of the Bayes estimator, which is the Bayes estimator is the average with respect of the posterior distribution of this estimator. Or I can define the Gibbs generalization error, which is the mean square error of posterior samples. And the Bayes generalization error is the optimal one. It's the best you can do in this kind of data set, because the student knows everything and is the best estimator possible. In particular, the Gibbs estimator is twice the optimal. The Gibbs error is twice the optimal error. So there are known results in this setting. And both of them, I would say, both the one I'm presenting here are kind of negative results in terms of feature learning, which is the thing I would like to study instead. So in the proportional regime, which is the regime where d is going to infinity and all the other parameters are scaling like d, it has been shown that this network I defined here is equivalent to a linear model. So it's not really learning the teacher, it's just approximating the teacher by a linear model, and it's learning the linear parameters. On the other side, in the interpolation regime, interpolation means that I'm in the regime where the number of points in the training set is the same or comparable with the number of parameters I have. In a very specific setting, when I have quadratic activation function and Gaussian prior over the inner weights, the network does not learn W0, but learn a combination of the teacher weights that is essentially a quadratic tensor, a matrix built with the teacher inner weights and the readouts. So you see that this is not really a result about feature learning, because feature learning in this setting would be learning W, learning the matrix that is embedding the data in the hidden space of the teacher. So is this a problem of this particular setting that has been chosen, or it's a more general result? And I would say that in reality, more generally, the student is actually able to learn W. Let's see how. So you see, this slide is very similar to the one I showed you before. I would like to evaluate the average of the replicated partition function. To do this, I would like to know the law of the lambdas at given weights, replicated lambdas at given weights. I can always take them as Gaussian, as I did before. In this case, it's a conjecture. Nobody proved it yet. But this is much more problematic than before, because now the covariance of the pre-activations is not a quenched random matrix V-shirt easy to study, but it's a order parameter. It's something that depends on two replicas of the student. And it's an order parameter that is a big matrix, because kappa k is going to infinity as well. And these kind of problems are hard to tackle from the point of view of statistical mechanics. And these are some early attempts that are not always matching with the numerical results. Given that, I can still do the same passages as before. So I can evaluate the kernel KAB as doing, let's say, this trick of averaging over the pre-activations. And these are still Hadamard powers of this more complicated matrix, which is now depending on two replicas. And again, I can write everything as an infinite series of scalar order parameters with Hermite coefficients entering in that way. And again, these order parameters I can interpret as overlaps between tensors with L indices, okay, where the tensors are defined as before, is the readouts times a tensor product of the inner weights. Okay, notice that here, because of the fact that the teacher is the same as the student, you can think of this as teacher-students overlap. If you take the replica 0, for example, and you name it as the teacher, replica 0 against replica 1 is telling you how much the student is aligned to the teacher. So, okay, as before, as long as this is written as an infinite series of order parameters, I can do very little. I have to find a way to simplify this series and possibly arrive at the end of the calculation. So here I split the discussion in two. I first explain the case of homogeneous readouts. Homogeneous readouts, that means that I give to the student V0, and I fix it to 1. Okay. Now, let's look at these tensors that I wrote before. So S1 is a tensor with one index, which means a vector. I have a vector with d components. And I have this square data, which means that, let's say, information theoretically, I can perfectly reconstruct it. From the point of view of statistical mechanics, it means that the entropy of these order parameters is negligibly small in the limit I'm considering, and so this order parameter is fixed to 1. This is for S1. SL with L greater than 2. So these are tensors that are a lot of components. So I need, if I want to learn them as tensors, I need at least D to DL data to learn them. But I have only ordered D square data. So there is no way I can learn this tensor unless the model realizes in some way that these tensors are not really tensors, but are all coming as tensor products of the teacher's inner weights. Which means that I'm saying that the overlaps, teacher-student overlaps for L greater than 3 are just powers of these more fundamental order parameters that is measuring how much the teacher and the student's inner weights are aligned. Okay? So if the student doesn't know anything about the inner weights of the teacher, then this quantity is 0. And so all the QL are 0 as well. Instead, when the student starts realizing some information about the inner weights of the teacher, then these quantities scale like powers of this more fundamental order parameter, and this power is the right one to give the right number of W's inside there, and everything works. And then I have S2, which is exactly the one with the right scaling with the number of data. And this is highly non-trivial, and I have to keep and explain how to do in the next slide. This is fine. Next slide. What do we do with S2? Well, S2, the distribution of S2 at given QW is this big formula. Here, I'm not saying anything particularly intelligent. This delta is fixed in the definition of S2, which is just this combination of matrix. Remember that here V is equal to 1, otherwise here I would have a diag V. But then I have to integrate also the definition of the order parameter QW with PW, which is the prior of the inner weights. So this is a distribution of a couple replicas of the random matrix S, and it's very difficult to deal with. But I can evaluate the exact second moment of it. The exact second moment in the asymptotic is given exactly by that thing, which means that I can relax that measure to a measure that I can instead use to do calculations. I can substitute the original measure with a measure where the prior of the matrix S2 is not the true one, but it's just a prior over the law of a Fisher matrix. And then I have an exponential tilt that I fix by moment matching. So I want this relaxed distribution to have the same second moment as the true one. And with this assumption, I can do calculations and I can solve the theory. So wrap up of the theory, because it was a bit complicated. Let me explain what I said. So I have two order parameters that are fixed via statistical mechanics approach, mean field saddle point, if you want. Q2 measure the alignment between this combination of the teacher's weights and this combination of the student's weights. While QW measure the alignment between the actual parameters, W0 of the teacher and W of the student. And then the theory predicts that for low alpha, so when the alpha is the number of points over the number of dimension squares, for low alpha, when data is scarce, QW is 0. So there is no real alignment between teacher and students, but Q2 is different than 0, which means that the students is learning as a polynomial model, as a quadratic polynomial model. And the theory is universal, so it does not depend on the prior PW. On the other hand, when I have more data, more than a certain critical value alpha specialization, I have both QW greater than 0 and Q2 greater than 0, which means now that the teacher and the students are actually aligning. So the students is really learning the features of the teacher. Let's see how the theory looks like. You see that, for example, look at the ReLU case. You have a curve for the generalization error that follows, let's say, the best that a quadratic model can learn out of a quadratic model. But then you have a specialization, which is a sudden drop of the generalization error, because now the student is really aligning with the teacher and is doing better than instead a polynomial model. And below, you have the same case with the tan H. Tan H has this characteristic that it doesn't have the second Hermite coefficient. And so it is not learning anything in the polynomial regime, because there is no component S2 to learn. But then there is a specialization transition when indeed the student is essentially learning everything because he is aligning with the teacher. And this is a check of the order parameters. You see that before the specialization phase, you have a non-trivial Q2 but all the other parameters to 0. Look at the y-axis that is changing between the two panels. And here I am above the specialization transition when Q2 is also non-trivial, but all the others QW are just powers of QW. Okay, maybe I have a few minutes to explain the non-homogeneous redoubts, which means that for the moment I looked at this setting. In reality, you have this setting where V is extracted from a certain prior distribution. And you see that it's not reasonable to believe that all the hidden neurons are specializing with the same amount of data, because you have much more signal about neurons that are linked to bigger readouts, essentially. And this you see even in numerics. If you look at the overlap matrix between teacher and student, and you look at different amount of data that you have, you see that if you increase the number of data, you have this kind of signal that is moving from neurons with bigger readouts. Here the neurons are ordered from bigger to lower readouts. And you see that you have this kind of signal that is expressing non-homogeneity in the specialization. We can still solve the theory in this way. We just need to, let's say, generalize a bit the order parameter to keep track of the readout to which the neurons are linked to. And so you see this by looking at the sum where the indices are now specialized to the case where the readouts are equal to certain values. So you write the same theory as before, except now that the parameters QW is a functional order parameters, depending on the values of the readout to which the neurons are connected. You can solve the theory as well, and you see these nice plots where, for example, for Gaussian readouts, you see that the weights that are linked to small readouts are not specialized yet, because this is the QW for those weights. But then the weights that are linked to bigger readouts start specializing according to the number of data you have. And these are results on generalization similar to the ones before. So we can say that something about hardness as well. So by looking at the trajectory of stochastic gradient descent, we see that for uniform V, for homogeneous V and binary V, there seems to be a hard phase before specialization. While for V Gaussian, our numerics is inconclusive for the moment. It could be hard, but if it's hard, it's with a very low exponent, so we don't know. And so it could be that specialization, in the sense of the phase transition I presented, is a hard phase transition, at least for certain target functions, the ones with the homogeneous or binary readouts. I'm over. I just said that for low alpha, the student learns, let's say, the best quadratic approximation of the teacher, but not the teacher itself. And this is similar to kernel machine. The mechanism by which it learns is slightly different because it needs to align these random matrices, while for kernel machines, you only have the readouts and it's easier. And for I alpha, you have this specialization phase transition where the student learns W, and so it learns the features, which is these hidden directions in the Ws. And that's it. These are the people with whom I did these works.
Thank you, Mauro. Are there questions? Don't wait for my first question. I'm part of the authors, so I won't ask one, so someone should go for it.
So you mentioned so I'm referring to the first part of the talk. You mentioned a few related work, but I wonder if you could put that in context, for example, on results on the polynomial regimes for random feature models. So for example, Theo has a paper where he looks at the polynomial regimes and he gets a picture that seems qualitatively similar to the one that you have. So I was wondering if you could spend a couple of words to compare the kind of results.
So I gave some references here. I'm not the best person to give an exhaustive review of the literature. I know that there are references that came out after my work, actually. For example, Misiakevich went on working on this. And
yeah, so that's the one I'm referring to. So this is the same regime, or is it different?
So it is the same regime. And it's interesting because, so in this setting, I was looking at a random target function, so a polynomial with random weights, while he's looking at a deterministic one. So I'm referring to a paper by Misiakevich that came out in March 2024, I think.
Yeah, I think that's the one.
Which is 2 months later than us. So he was working on parallel in this. But
how does it make a difference, having a deterministic versus a random target?
It doesn't. I mean, it's very similar. The approach is different. We are using replicas. He's doing formal stuff. But he writes everything in terms of a few equations that solves for order parameters, in some sense, that are comparable to the ones we get in the replica setting.
Are they the same?
Sorry?
Are they the same?
That I don't know. I haven't did the mapping precise.
Thanks.
What can you say when you have a teacher and students with different number of hidden units still in this proportional regime?
In the case, in which case?
I was thinking about the first case, but if you can say anything about the second case, that would be interesting too.
So in the first case, the thing I'm saying is that whatever I put here, so here I could put a neural network, for example, instead of a polynomial directly. And by putting a neural network, I mean that I could take the same distribution, the same architecture than the student, but with the lower, for example, with the neurons. So I guess that because here the student is learning as a polynomial model, I guess that it will learn the polynomial, the best polynomial version of the teacher, I would say. Unless the number of directions of the teacher are much low, are much less. So if I have a finite number of hidden neurons for the teacher, then it means that I have very few features, and that can change stuff.
So you don't see a clear difference in behavior between an overparameterized and underparameterized regime in this case, in terms of complexity of the rule? So
in terms of complexity of the rule.
But this is one way we look for overparameterization. We take just a number of hidden units in the student to be larger or smaller than the teacher. But in this case, it seems that this will give qualitatively the same behavior.
Well, if you are underparameterized in the sense that you have much less parameters than the number of parameters of the teacher,
of the same order.
You just don't learn the higher order terms, in some sense.
Yeah, okay.
So the degree of the teacher B is not particularly interesting. It's just telling you that if you have a student that is that has more parameters than B, then you can learn perfectly. Otherwise, you go to a plateau, which is the best you can do.
Okay.
But this is a consequence of the way I chose the polynomial defining the teacher. Because you see that here, these objects are homogeneous tensors because they are taken IID Gaussian with order 1 elements. So the way also you learn by staircase is due to the fact that you have few order 1 vectors, element, much more order 2 tensor elements, and so on. So you need to have this well-defined hierarchy of features in a sense. With a teacher with few parameters, I don't know. I haven't thought about it.
Is there a last question? Okay. If there's not, let's thank again Mauro.